Hey guys, this is Mr. Larson. Today we're going to talk about 1.9, which is inverses. You studied this in Math 3, but we'll kind of recap and then go a little bit deeper into inverses. If you have two functions, one's g, one's f, we say that the function g is an inverse of f if g reverses f, or if it undoes f. Okay, think about if you're solving an equation. Let's say you have like x plus 3 on one side and you want to get x by itself. You're going to subtract 3. Right? Because addition and subtraction are inverse operations. The subtraction would undo the addition. So that's kind of the idea with inverses. So let's look visually. Here's three separate examples. You'll see in each of these, the light gray is the original function. We'll call it f of x. And then the black is the inverse of f of x. We say f to the -1 of x. So anytime you have two inverses of each other, or a function and its inverse, this slanted line, this diagonal line that's cutting through the first quadrant here is the line y equals x. Okay, so we can see that these functions, when they're inverses, are going to reflect each other over that line. So you can visually see or visually prove that functions are inverses if they are reflected over that line y equals x. So there's two examples. Here's another one with our x squared and square root function. We can see those are inverses because they are reflected over that line y equals x. Okay, we're going to see another example on Desmos a little bit later that kind of looks at that a little deeper. So I'm going to let you guys do a warm-up. I'll walk through the first one, then you guys can try the other 5, and then I'll show the answers here. So just to recap from last week, f of g of x. First, we switch our notation. Then we start on the inside and we substitute the expression that's equal to g of x, which is x minus 3, which means we go to function f and we plug in x minus 3 for our input, and then we simplify. Okay, so go ahead and try those other 5. You can pause this and then come back to see the solutions. Oh, look how quick that was. Okay. All right, so let's move on here. So let's talk real quick. Remember, the vertical line test is how we check to see if a graph was a function, right, or if an equation was a function. We can do the horizontal line test, which works the same way, except you hold horizontal and you just kind of move up and down. That's going to determine if a graph's inverse is a function. Okay, we use this term one-to-one if a function passes the horizontal and vertical line tests. And then we talked about that function and its inverse will be reflections over this line y equals x. And the reason that is the case is because a function and its inverse take their inputs and outputs and switch them. Okay, so y equals x. Your y becomes your x becomes your y. They just kind of switch. Okay, so that's how I remember what they're reflected over. Y and x switch. Okay. So let's take a look at a few functions here. Let's determine if the original graph is a function, and then if it has an inverse, that's a function. So this first one, f of x equals the square root of x. By the way, when you have a square root function, let's strategically pick values that are going to come out as nice numbers. So let's plug in perfect squares so that when I take the square root, they're integer values. So 0, square root of that is 0. Square root of 1 is 1. The next perfect square is 4, so the square root of that is 2. And there's our graph. Vertical line test tells me that yes, the one I'm looking at is a function. Horizontal line test, right? I'm never going to hit in 2 spots at the same time. So it passes the horizontal line test. So yes, its inverse is also a function. Okay, I'll do one more. You guys can try the third one. Okay, let's plug in 0. Let's plug in 1. I can also plug in -1. 2 squared gets me 4. -2 squared also gets me 4. Okay, so we can tell that this is going to pass the vertical line test. So yes, it's a function. But when I do the horizontal line test here, we can see that that's going to hit in 2 spots anywhere above the x-axis. So no, its inverse is not a function. Okay, you guys can try one for execute. Hopefully that makes sense. All right, so this next part, we can find inverses of functions algebraically. We don't have to just look at a graph and try to determine if it's being reflected over y equals x. So here's kind of our process. The first thing I want to do is take out f of x and just change it to y, right? They mean the same thing, they're both outputs. Then I want to switch y and x. We're literally going to switch the positions. Then we're going to solve for y, and we're going to put in our inverse notation. So change this to y equals 5x plus 2. Switch the positions of x and y. Solve for your y value, so subtract 2. And we divide by 5. I'll put y on the left side, x minus 2 over 5. And then lastly, let's put in our inverse notation. So I say the inverse of f is equal to x minus 2 over 5. Okay, let's do the same thing on this second example. So y equals square root of x minus 4. Switch the positions of your variables. Solve for the new y. So I need to get rid of square root. So I square both sides. And then we add 4. I get y equals x squared plus 4. Lastly, put in inverse notation. Okay, let's take a look at these two examples. So first I'm going to look at f of x equals 5x plus 2 and its inverse. So we see those graphs here. The original function is red, the inverse is blue, and what I've also put on here is this line y equals x. So we can see visually these two are reflected over that line. Okay. Now let's look at that second one, which was y. I think f of x was x minus 4 under the square root. We said our inverse was x squared plus 4. Okay, so let's look at these two. Now, these don't look like reflections to me, and they shouldn't because they're not, right? Part of it's a reflection, but we can see this orange one looks like it's got a lot more to it. So what I want to do is let's limit the domain, and I'm just going to shift this so that visually it's hidden. But if I limit the domain to just my positive inputs on this orange graph here on my inverse, now I can see that those are reflections of each other, okay? And let's think about why that is. Well, when you have two functions, if you have a function and its inverse, let's think about domain and range of my original function. So for f of x, my domain, let's see, I would have to be 4 or bigger, right? So from 4 to infinity. Once I go to like 3 minus 1 is -1. Taking the square root of that, that's where I'm going to generate some imaginary numbers. Okay, so the domain is from 4 to infinity. The range let's see, out of a square root, coming out of a square root, you're either going to get 0 or positive, because I'm not doing plus or minus. So the range on this is going to be from 0 to infinity. Okay, when I look at its inverse, right, here's the inverse of f of x. We're saying the x and y values are going to switch. That's how you get that reflection. It means that the domain from f of x is going to be the range in the inverse of f of x. And the same will be true. The range from f of x will become the domain of the inverse. Okay, so what I'm saying is that the domain of my new function, my inverse, is going to be the range from the original. Okay, so this domain should be equal to the range from f of x, so 0 to infinity. Okay, now when I do that, if I just look at the domain of this original function, I can plug anything in there, right? I don't have any fractions with x. I don't have the square root of anything. So if I'm just saying what's the domain of that function there, it would be from negative infinity to infinity. But in order to get the reflection over y equals x, I have to limit the domain on this function. Okay, it's the only way you'll get that reflection. And the other way to remember it is just remember the domain of your inverse is going to be the range from the original function. Okay. All right. Last thing we're going to do, we can take these two. Let's look at this first box here. So if I look at these two functions, let's call the inverse g of x for right now. If I compose those two functions together and simplify, let's take a look at what happens. So what I mean is let's do f of g of x. Okay, we're composing these two functions. So f of, let's see, g of x we're saying is x minus 2 over 5. So go to f and plug in your new input. Y's cancel. I'm left with x minus 2 plus 2, which simplifies to just x. Okay, interesting. Let's do this the other way. Instead of f of g of x, let's compose them in the opposite way. So g of f of x. So g of 5x plus 2. Go to g. Remember, I'm calling this one g. So that's 5x plus 2 minus 2 over 5. Let's see, that just gives me 5x over 5, which simplifies to just be x. Okay, interesting. So why did I get this result? Why did this happen? Why did this happen? Let's think about that. When I composed two functions that are inverses of each other, they simplified to just be x. When I did the other way, it also simplified to be x. Well, hopefully that makes some sense, right? At the very beginning, what did we say the definition of an inverse was? Didn't we say that if f and g are inverses, they would basically undo each other, right? How did we word that? A function g is the inverse of f if g reverses or undoes f. Well, that's what's happening, right? This function f from this example is starting with x and it's doing something to it, right? It's multiplying it by 5 and then it's adding 2. Well, when I throw this other function in the mix, it's going to undo all that stuff and you're just left with x. Okay, so if I said, here's two functions, prove that they're inverses, you can simply compose them in either way and see if it simplifies to be x. Okay, both ways, f of g of x and g of f of x should come out to just give you x. All right, so that's why we got that result. By the way, if we look back at this third column here for the warm-up problems, I did f of h of x and h of f of x. What do we notice that these each simplified to be? Well, they both came out to be x. So we can conclude from that that f of x, which was 3x plus 1, and h of x, which was x minus 1 over 3, are inverses of each other. All right, guys, thanks for watching.